very good morning, students. So, welcome. This is the class for Mathematics 2 of JNTUH B.Tech course. And in this syllabus, the last 2 units belongs to vector calculus. These are the most important units, and this video lectures belongs to only we are concise up to the examination point of view of your B.Tech syllabus in exam point of view, right? So that's why we are not elaborating each and everything, and we are not going to give the detailed definition in terms of physical meaning and not like that. So again we will do some more lectures in a detailed way, but these lectures will help you for the preparation of coming examinations, right? So in that way, the vector calculus, in this vector calculus we are having 2 units. One is, that means according to syllabus, this comes under unit 4. This is vector differentiation. And unit number 5, it is vector integration, right? So now today we are going to start this unit number 4, that is vector differentiation. Okay, right, let us start. A vector differentiation. So all of you know there are 2 things. One is a scalar quantity and another one is a vector quantity. So the difference between these two, this scalar quantity having only magnitude. So here in this vector quantity, this combines both magnitude and as well as direction. So these are the difference between a scalar quantity and a vector quantity. Suppose there is a mass. So this is having a mass which is having only a magnitude, a mass 500 grams, a mass 1 kilogram, a 200 grams. Only a magnitude, that quantity having only magnitude. But suppose this is a mass. Suppose this is a mass m. This mass I am going to pull it, or I am going to push like this, or push from bottom, push this side. So that means I am going to apply the force on this mass. So when I am applying the force on this mass, So according to, suppose if we are applying the force from the left hand side, then this mass is moving in this direction. So when I am applying the force from this direction, then it is moving this direction. So therefore here two quantities, if you are observing, this is having both magnitude, this represents the magnitude and this represents the direction. So therefore a force applying on a mass, so along in which direction that mass, that magnitude is moving. So it includes both magnitude and direction. This is called a vector quantity, right? Now here the most important 2 points before going to the actual topics. So these are the topics in this unit. So first I am giving unit number 4 topics. So I am going to divide all these topics into maximum 2 parts. One is, so part 1 belongs to scalar and vector point functions. The next topic is gradient, divergence and curl. The next topic is tangent plane and normal surface or normal line, tangent plane and normal line. So the next part in the same unit, the most important vector identities, also the scalar potential function. So here again I am writing, and this is a scalar potential function. The same thing we can discuss in this first part only, scalar potential function. So the second part belongs to only here again I am writing, so normal line. The second part, and in the first part scalar potential function. The second part belongs to only vector identities. Okay. So this is the first part and this is the second part. So basically in the starting of the class I discussed purely this is up to for examination purpose, right? So this chapter is most important and it is very easy chapter for this total mathematics 2 syllabus, mathematics 2 course. Okay. So now, in the first part, before going to first part, first we are going to see some definitions in this way. The first definition is position vector. What is meant by a position vector? Suppose this is a two-dimensional plane, let it be x, and this is y-axis. So along this x-axis, along this y-axis, there is a unit vector I bar corresponds to x-axis, and a j bar is the unit vector corresponds to y-axis. Suppose let us take the point P, x comma y on this plane, and this is another point, this is a point 0 comma 0. Suppose from here to here, this is the direction, and the corresponding vector between these 2 points. So the corresponding vector, these 2 points, that means x2, this if you say this is x1 y1 and this is x2 y2, x2 minus x1, that means x minus 0 into I bar plus y minus 0 into j bar. This is equal to xi bar plus yj bar. So this is the vector xi bar plus yj bar. So this vector xi bar plus yj bar, xi bar plus yj bar, it is denoted by r bar, is called the position vector of the point P x comma y. So r bar is equal to xi bar plus yj bar is called the position vector of the point. So suppose there is a point P1. This is x1 comma y1. Suppose from here to here, let it be, I am calling this as r bar. Suppose let it be r1 bar. So if you take r1 bar is equal to x1 minus 0 I bar, that means x1 I bar plus y1 j bar is called the position vector of the point P1 x1 comma y1. So this where that point is located, where what the point is in the plane, what is the position of the point, so what is the direction. So here the most important, the position vector, we have to calculate the position vector where the tail of the vector must be the origin. So from the origin, that means from the reference point, that is the most important. Where that point is located, what is the position of that point, what is the vector corresponding to that point. So when we calculate the position vector, we must see the we must place at some we must calculate from the reference point. So here this origin is the reference point. Origin is the reference point. So from the origin, what is the position of that point? From the origin, what is the position of another point? So therefore, this vector is called the position vector. Now this is a position vector in a two-dimensional plane. Suppose if you take it is in a space, suppose it is in a space x, y and z. So I bar, j bar, this is I bar, j bar and this is k bar. Suppose let us take a point in a space, that means in a space there is a point. So let it be P, x, y, z be the point. Now what is the position vector of this point with the reference the origin? So the position vector of the point P x y comma z is, so x I bar plus yj bar plus zk bar. So always the position vector is denoted by the letter small r. So r bar is equal to xi bar plus yj bar plus zk bar. This is the position vector of the point xyz in a space. Right. Now, what is the magnitude of the position vector? The magnitude of the position vector. So when we calculate the magnitude, that means, so magnitude means from this origin to this point, what is the distance? It is nothing but the distance between 2 points. So the magnitude of the position vector, it is denoted by modulus of r bar. So modulus of r bar is denoted simply as r. So in a space, this is modulus of xi bar plus yj bar plus zk bar. This is equal to square root of x square plus y square plus z square. This is the value of r. This is the magnitude. That means from the reference point origin to the point P x comma y comma z. The position vector is r bar. The magnitude of r bar is modulus of r bar, which is equal to the square root of x square plus y square plus z square. Right. So now the position vector r bar we defined. What is the magnitude of that position vector? So this can be written as r is also can be written as x square plus y square plus z square power 1 by 2. This is most important. We are using every time whenever we are studying this vector differentiation and later vector integration. So you have to remember this one. What is the position vector? Right. Now, the next one, there are two important definitions. There are two important definitions. Are two important functions. So whenever we call it as a function, we are having a domain and a range, right? There are two important functions. The first one, which is a scalar point function. The second one is vector point function. So there are two types of functions. One is a scalar point function and another one is a vector point function. The most important functions in a vector calculus, right? So we are mainly dealing with these two functions, scalar point function and a vector point function, right? Now we will see the first one, scalar point function. So suppose when I am considering this is a two-dimensional plane, x and y axis, this is my reference point. So this is my point P. There is a point x comma y, and this is called the position vector r bar corresponding to this point. So generally I am writing as P represents the point, r bar is the position vector corresponding to this point P. So this is the position vector corresponding to the point P. P is the point, so this means P is the point with position vector r bar, right? Suppose there is a point in a plane. Suppose I am considering a point. There is a function. Suppose this is a function, this position vector r bar having a function which is a function, let it be f. This is a function f of x comma y. So for this function f of x comma y, because I am dealing in two-dimensional plane, any point in this plane, this function always gives a scalar quantity. Then that type of, so for every point in this coordinate plane, this function gives us a scalar value. And by the way, for every point in this coordinate plane, we are having a position vector. So you have to remember that one. And for that point, Suppose there is a function. From that function we are always getting a scalar quantity, then that function is called a scalar point function. That means so there is corresponding to this position vector. So already this is my P of R bar. This is my R bar. So there is a scalar quantity. Suppose I am for this position vector, there is a function which is, suppose let it be phi of R bar. So for this function always we are getting a scalar quantity. That function is called a scalar point function. Suppose, for example, I am going to consider phi of x, y in a two-dimensional plane, let it be. So for this point there is a position vector. So this is phi of R bar, the corresponding position vector for this point phi. So there is a function, suppose let this function be x square plus y square. So every point the position vector, if you are observing this one, this is for this position, this is x square plus y square. Suppose this is the radius, if you take 1 and this is 1 at this position, at this position, at this position, it represents a circle. So for every point, we are getting a unique scalar value. That what you have to remember. For every point there exists a unique scalar value. That function is called a scalar point function. Suppose let it be, I am going to take point phi 1 comma 2. So this is 1 square plus 2 square. This is equal to 5. So unique scalar value, that function which is called a scalar point function. Now another important function, this is a vector point function. So this is, whenever we call it as a vector point function, this is a direction and at the same time having a magnitude with a scalar. See, let us see. Suppose I am having, suppose this is a two-dimensional plane, x-axis and y-axis. I am having a vector, let this vector be v bar. Suppose this is cos t I bar plus sin t j bar. Suppose this is a vector. Suppose here I am writing v bar is equal to cos t I bar plus sin t j. Now this t represents a scalar variable. Suppose this is v bar, it depends upon a scalar variable t. So this is defined by cos t I bar plus sin t j bar. Now let us see. Suppose when t is equal to 0, what is v bar of t? Which is equal to I bar. Now see, when t is equal to, when the initial value of t is equal to 0, this is I bar. in this direction. Suppose when time t is equal to, suppose if you consider if you take in radians, so suppose time you can take into radians, suppose cos 30 or cos 60 if you convert into radians. This is what when t is equal to 60, suppose let it be 60, cos 60 1 by 2 sin 60, so which is root 3 by 2. Then what is this point? At this point when t is equal to some 30 degrees or some 60 degrees, it is in this way. So when t changes, it changes its direction. When t changes, it changes its direction. But if you are observing, what is the magnitude of this vector? Modulus of v bar of t, which is equal to the square root of cos square t plus sin square t, this is equal to 1. So this is all having with a unit radius. This is a point, this is a point when t is equal to something. Suppose this is when t is equal to 30 degrees, when t is equal to this is some 60. So when t is equal to some 90, this is when t is equal to 0. So at that particular value of t, this is the corresponding vector in this direction. At some t is equal to this one, this is a vector having this direction. Suppose when t is equal to 0. So what is this one? When t is equal to 0, what is going to happen? Cos 0, 1. So what is when t is equal to 0? This is 1 into I bar plus 0 times j bar. Suppose when t is equal to 30 degrees, so what is v bar of t? If you convert into radians, v bar of cos 30 root 3 by 2 I bar plus 1 by 2 j bar. So this is the direction, root 3 by 2 comma 1 by 2. But in the scalar point function, we are getting only unique scalar value. But along the scalar, what is its scalar value? If you take the magnitude, magnitude is always 1. If you take any magnitude, it is always equal to 1. But it has some direction. So for every value of t, for every value of scalar, we get a direction. We call this root 3 by 2 and 1 by 2, these cos t and sin t, those are called components of the vector. So mainly or crudely we are speaking a scalar point function. There is no vectors I bar and j bar. In a vector point function, there is I bar and j bar. So just you remember this point. Okay. So we are having 3 definitions. What is meant by a position vector of the point P, P of r bar. The second one, the scalar point function. Generally we denote it as phi of x, y, z. The third one, a vector point function. Generally it is denoted by f bar of x, y, z. So this is equal to f1 I bar, f2 j bar plus f3 k bar. So these are the most important definitions, right? The next definition very important definition, which is level surface. Level surface. So, the definition of the level surface, it is the surface formed by the set of all points, I am calling it as a surface. So, therefore, we can deal in a space, in a three-dimensional plane. If we call it as a plane, then it comes under 2D. So, when we call it as a surface, by the set of all points x, y, z satisfy the equation phi of x, y, z is equal to constant, then that function phi of x comma y comma z, then phi of x comma y comma z is called level surface. So, the level surface is the surface formed by the set of all points satisfying this condition, this equation phi of x comma y comma z is equal to constant. Suppose this is my surface, this is the surface. So, the set of all points satisfy some constant, then it is called a level surface. Suppose let us take some example. Suppose if you consider you are sitting in a class having some room temperature. So, all the 60 students sitting in a class, so all the students, 60 number of students in a class, this class having a room temperature, suppose let it be 28 degrees centigrade. So, therefore, this is the temperature of this class. Now, suppose at this point this is a student. For this student, what is the temperature? Suppose let it be a point 28 degrees centigrade. There is a student. What is the temperature of this student? This is also 28 degrees centigrade. There is a student at this point, what is the temperature of the student? 28 degrees centigrade. So, here the temperature is at any point in this class, which is equal to some constant. So, here in this, the temperature is called the level surface, because at every point in that class it is equal to some constant, let it be 28 degrees centigrade. So, therefore, this is called the level surface, right. So, the three important definitions, again I am repeating. The first one is the position vector, second one is a scalar point function and a vector point function, and the next one is the level surface, right.